In this slide, uh, I'm going to propose a scalable capacitor structure for 3D cross-point memory. This is the current solid-state drive system. Here's the data bus, microprocessor, DRAM, and NAND are connected here. When the data which is required for processing located cache memory, then the data read or write operation can be done in a 1 millisecond, 1 nanosecond in this example. When your data doesn't exist here, then you have to look for that data in DRAM. If that data is located in DRAM, then you would need to take more time, such as an order of 100 nanosecond for read or write operation. This is called cache miss. Then the cache miss rate must be minimized. When the data is not presented in DRAM, you would have to look for that data in NAND. When you want to write the data into NAND, then the NAND needs much more time, such as 2 milliseconds. As a result, the access time in this case is limited by NAND write operation. When the cost is normalized by a unit of NAND chip, and if your system has 20 NAND chips, then the storage cost is 20. So cost of 20, whereas the access time of 2 milliseconds at max. The SSD providers are thinking about the upcoming SSD system, which has much faster access time 3D cross-point memory on the drive. You don't have to replace all NAND chips with 3D cross-point memories, because you just need to accelerate the performance with minimal overhead in terms of cost. In case the data you are looking for doesn't exist in DRAM, then you would have to write the data into 3D cross-point memory first. Suppose the data size is 16 KB, then the total write operation is estimated about 60 microseconds rather than 2 milliseconds, which is 1% of NAND write operation. So you can get much higher performance with 3D cross-point memory. In terms of the cost, when the 3D cross-point memory cost is 10 times as large as NAND cost. And if you replace a single NAND chip with a single 3D cross-point memory chip, then your storage system costs 29, which is 1.5 times as large as the previous or existing SSD. And so in this example, you will have another option with the 50% higher cost for storage. You could get the higher performance of 100 times better. So let's look at the structure of 3D cross-point memory. 3D cross-point memory has multiple word lines and multiple bit lines. Word lines and bit lines are placed in perpendicular each other. In between, you will have a non-volatile memory element at the cross point. As you see, when you stack more layers, then you will have more bits per area. So suppose you will have the design rules such as the width and the space for word lines and bit lines kept the same across many generations. Then your bit density should be increased at the rate of the number of layers. This can be considered as effective Moore's law. Do you have any issues to be addressed with the 3D cross-point memory? Yes, there is. Because if we want access more bits when you increase the number of stack layers, and your word lines and bit lines must be driven by boosted voltages for write or read operation. And that current for boosted voltages provided by on-chip boost converters. And on-chip boost converter has relied on on-chip capacitors whose capacitors density is given by the gate oxide of transistors. As long as your supply voltage remains the same, such as 1.8 volts, then your gate oxide thickness is also constant. Therefore, if we want to increase the drive current at the same rate as the number of layers of cross-point memories, then you have to increase the capacitor area, which also increases of course, die size, and which increases the cost. This is a problem because the original concept for the 3D cross-point memory is keep the area for array, but increase the density per area. Thus, even if you can do that for array side, but you cannot do that in for the periphery area due to significantly increased capacitor size. And then here we propose scalable capacitor structure like this. So because we have the multiple word lines, bit lines, layers in memory array side, why don't we keep that structure in the periphery side without memory element? So suppose if you fully remove non-volatile memory element from periphery area, whereas remain the meta layers for word lines and bit lines, then you will have a scalable capacitor structure in the periphery side. So I call the scalable because capacitance of this structure increases at the same rate as the number of layers, which is fit with the uh, parasitic capacitance of memory array. So requirements like this, uh, wiring layers for word lines and bit lines used for capacitor terminals, non-volatile memory material removed, no increase in process steps. The last item is ideal case. So probably the target is to minimize an additional process steps for making this structure in the periphery second. One example uh, for the how to uh, implement that structure is like this. You place CMOS in the memory array side and also periphery side. The transistors in memory array side will be transistors for decoding circuits or sensing amplifier. So after first word line patterning, you will have the non-volatile memory element in the memory array, but that material should be removed from the periphery area. Then you will fill the vacant region with insulators such as SiO2. Then you will put the first bit line layers in patterning, and afterwards the similar steps continue up to the top word line or bit lines layers. Here's the final the structure, and you will have the scalable capacitor in the periphery region. This is the estimate how you can get with proposed structure in terms of die size overhead. Let's assume we start at 3 word line bit line layers, which has 5% die size area impact for the boosting circuit. And assumptions are existing technology is 4 nanometer gate oxide for 1.8 volt CMOS, which has a capacitor density of 8 nanofarad per millimeter squared. For the proposed capacitor structure, we assume a 20 nanometer technology node for word lines and bit lines patterning. As the number of word line bit lines layers increases, the your gate oxide capacitor must be increased by the same rate, whereas there is no additional overhead with proposed structure. So this area overhead uh, is resulted in the chip die cost. This figure shows the number of word lines and bit lines 3 to 9 transitions if we have same die side with existing technology and proposed capacitor structure. With the 9 layers, existing technology require additional 10% die size increase, which is equivalent to cost increase of 10%. If you don't have to add any process steps to make that capacitor structures in the periphery circuit, then there's no cost overhead with the proposed circuit capacitor structure. So this difference increases as the uh, technology is more advanced. In summary, in this presentation, I proposed the scalable capacitor structure to reduce the cost of 3D cross-point memory, which will be used as a buffer memory for NAND flash memory, which is considered 5% of NAND die market will be replaced with 3D cross-point memory, which is of course huge. I believe this idea contribute to semiconductor industry. That's it. Thanks.